The warm-up question says, Mr. Rocco is done showing off his mad skateboarding skills when he coasts to a stop from 1.2 seconds to 3.4 seconds as shown in the graph. So you can see here that there is acceleration occurring in my XT graph where we have this curve. The green portions are showing constant velocity. It says find his acceleration during that time and find his stopping distance. So we have a couple of calculations to do, but we have to get some of our data from our graph because it's not really given to us in the question. So let's go ahead and take a look at how we could approach this. So again, we're trying to solve for acceleration and stopping distance. So the first thing we're going to want to do is label the information that we've been given. So looking at this, obviously they gave us a time. We know that the time over which this acceleration occurring is from 1.2 to 3.4 seconds, which is a time range of 2.2 seconds. So the time over which this acceleration is occurring is 2.2. All I did was subtract those two values. But that's the only thing written in the question. So what other information do we know? Because the only other thing we have is the graph. So what can I tell by looking at my graph? This is a position time graph. Okay, so what can I figure out about his motion by looking at this graph? Sure. Okay. What else? Can I tell how fast he's going? Yeah. Or silent today. Yes, we can tell how fast he's going. Okay, we know that because on my XT graph, my slope is my velocity, and the green portions represent constant velocity here and constant velocity, or rather zero velocity here. And so I know that my final velocity is zero because it says he goes to a stop, first of all, and then you can see it in the graph as well. Okay, so we know the final velocity, but the initial velocity I can get by just looking at the slope of this line and doing rise over run, okay? Change in y over change in x. And for this straight line segment, that's 15 over 1.2 because in the first 1.2 seconds, he goes 15 meters and he does so at a constant velocity. And so if I divide those, I get his initial velocity before he starts to slow down. Okay, so looking at my graph, I can find the slope of the line segment to get his initial velocity, the slope of the line segment to get his final velocity, although that's just horizontal, so that one's a lot easier. And so now I have initial velocity, final velocity, and time. Somebody did say displacement, which yes, I can see that kind of. It's kind of hard to see exactly where the line is though, at the top is the problem. Okay, it's because of the way it's numbered and how thick that line is, it's really difficult to tell what my displacement is. I can get a rough idea, okay, but I probably wouldn't want to use that in my calculation because I can't tell exactly what it says. Okay, if it was a graph with more markings on it, then maybe. Okay, or if it was on the grid line, then definitely. Okay, but because it's not there, let's go ahead and not use that number because we don't know exactly what it is. Okay, but we do know time, we do know final velocity, we know initial velocity, and from that, we can certainly calculate both of these two things. Okay, delta x, my displacement, or how far he goes during that time, that would be his stopping distance. Okay, and then the acceleration that he undergoes as he is slowing down, we can solve for both of those. And so we have these different equations that we get to use in order to solve for these two variables. And so if I want to solve for delta x first, I guess since I listed it first, if I take a look at the things I know, time, final velocity, and initial velocity, and I'm looking for displacement, the equation that has those variables in it would be equation D. Because there's my VI, there's my VF, there's my time, I would be able to substitute in and solve for delta x. For acceleration, if we wanted to solve for that one first, we could use equation A because there's my final velocity, there's my initial velocity, there's my time. Okay, so you can solve for either of them first, but we're going to go ahead and actually I solve for acceleration first. So we're going to go ahead and solve for the acceleration first using this equation. VF equals VI plus A times T. We're going to solve for that variable right there. We know all of the other three. So, and then this would be one way to solve for delta x, the other would be equation D. You could do it with either one. Apparently I did it with that one. Okay, if you wanted, you're going to solve for the acceleration, you can then use it for that one or use the other equation. Okay. So if I plug in solving for acceleration first, there's my final velocity, there's my initial velocity, plus a times t. This just becomes an algebra problem. I need to isolate my variable a, and so I'm going to subtract 12.5 from both sides. Okay, that's going to give me negative 12.5 over here equals 2.2a. And then if I want to isolate a, I need to divide both sides by 2.2. And that gives me an acceleration of negative 5.682 meters per second every second, or meters per second squared. So that would be the rate of acceleration over this time period represented by the red curve. Okay, is negative 5.682 meters per second squared, or meters per second. Again, you should be putting this in my open math. All right, so that's the first part. The second part is his stopping distance. And again, I can find delta x with more than one equation. Because I just found acceleration, I can use this one. If you want to use the other one, that's fine too, because we could have done it either way. But with my example, I have it with this one. Delta x equals vi times t plus 1/2 times a times t squared. 12.5 times 2.2 is 27.5. Half of negative 5.682 is negative 2.841 times 2.2 squared, which is 4.84. Again, if I multiply those, I get negative 13.75, and that's a negative number plus 27.5, so I'm really subtracting here. And I get a displacement of 13.75 meters. And yes, you can look at your graph and make sure that that makes sense, because he starts here at 15. So 13.75 meters is going to be a little less than 30, and it is a little less than 30. So that's where I would expect it to be, but it's hard to see exactly what number that's at. Okay, again, please make sure that you put this in the warm-up. I'm going to tell you guys right now, you have a test question that looks a lot like this. Okay, so you're going to have a free response question on your test that looks a lot like this. I would definitely make sure that you know how to do this. Make sure you know how to pull some data from your graph and use it in a calculation. And if not, look back at this. I think there's one in your My Open Math assignment today as well, so there'll be some more practice there. But you do need to know how to do this. Okay, so if you're not sure what's going on with it, please make sure you say something, make sure you ask, or come in for tutorials, something. Does anybody have a question about this? Okay. All right. So we've been doing some kinematic equations with acceleration. So calculations just like the warm-up. They don't always have graphs in them. And I introduced the new topic of free fall, so acceleration due to free fall, the other day. And so we're going to just go through some additional examples, but this one's a little bit different than the ones that we looked at the other day. It is free fall. However, today we're going to talk about examples of objects that are in free fall, but instead of just being dropped from rest, they're going to be thrown like this one. Okay, so whenever we did free fall before, everything had an initial velocity of 0 because we were dropping things. But they don't have to. They could be thrown, and that's still in free fall. As soon as you release it and you're not touching it anymore, and the only thing acting on it is gravity, now you are looking at a free fall problem. All right, so this one says a stone is thrown downward at 5.2 meters per second into a deep well and is heard to hit the water 2.41 seconds after being thrown. Determine the depth of the well. And so if we, I'm going to start with a picture. And I would recommend that you start with a picture as well for a lot of these problems. So here's my stone. Here's my initial velocity. It's thrown downward, and I'm going to go ahead and call that my negative direction. So I'm not just going to label it as 5.2, but I'm going to label it as negative 5.2 meters per second. The time is going to be 2.41 seconds, and we're looking for the depth, which means we're looking for how far down it goes. So we're looking for displacement. Okay. So again, draw a picture. Okay, that'll help you hopefully to identify your given information, but especially help you to make sure that you have the direction correct, the negative signs if you need them. Okay, so I'm given an initial velocity of negative 5.2 meters per second. I'm given a time of 2.41 seconds, and those are the only numbers in the question. However, this is a free fall problem. So although it doesn't say it, I also know my acceleration. What is my acceleration? I heard mumbling back there, but yes, negative 9.8 meters per second squared. It's not going to be written in the question. You just need to know it. Okay, so we also know that piece of information. Anytime we have free fall, we also know the acceleration. And so now if we want to determine the depth of the well, our unknown is delta x, now we have enough information to do it. VI, T, and A, we're looking for delta x. The equation we're going to want to use, and again, here they are, is going to be equation C. Because there's delta x, I can solve for it. Here's VI, T, A, and T. Again, I just can't pick an equation with VF because I don't know it. Now, could I solve for it? Absolutely. I just don't need to. So if I want to do it in the most efficient way possible, I'm going to use equation C that is labeled over there. Okay, so we're going to plug into this equation. Okay, so substituting in, we get this. Negative 5.2 times 2.41 plus 1/2 times negative 9.8 times 2.41 squared. Guys, be careful with your signs. Okay, whenever you do this, make sure that you get the right signs here, because if you don't, this is addition in between here. So really this ends up being subtraction over here. Okay, but whether you're adding or subtracting from a positive or negative number is going to give you a different answer. So check those signs, make sure they're correct. So whenever we go ahead and multiply these things out, we have negative 12.532 plus half of negative 9.8 is negative 4.9. And 2.41 squared is 5.8081. We can multiply those two numbers together and add it to this, and we get negative 40.99 meters. Again, my displacement's going to be negative because the rock is going down. Okay, so the depth of the well, you could report your answer as just 40.99, but if I asked for displacement, you would need to say negative 40.99 because we define that downward direction as negative. So again, you need to be able to do this. It's the same process. It's just now I have an initial velocity to consider. Okay, and it'll be given to you in the question. If it's dropped from rest, a lot of times it doesn't say the initial velocity is 0. It says it's dropped, and it's implied then that it's 0. So if they give you a velocity, you use it. If it says dropped, you use 0 for the initial velocity. This one, though, is a little trickier because you can also have an object thrown up into the air. And if you're throwing a ball up into the air, it's still in free fall. Okay, as soon as it leaves your hand, the only force acting on it is gravity. You guys, you're definitely going to want to write this one down. Okay, these are the trickiest ones for students. All right, it says a ball is thrown upward at 3.4 meters per second from the ground. What will be the maximum height that it reaches? And you can sketch a picture like this. We're assuming it's thrown directly straight up and down. It's just really hard to draw that, so I kind of stretched it out this way, but we're going to say it's straight up and then straight back down again. Okay, and we're looking for the maximum height, which you can see I've labeled here with this red arrow. So information I'm given, obviously I'm given an initial velocity of 3.4 meters per second. That is the only thing that I see in this question. And yet, I'm going to tell you right now, I have enough information to solve it. Because I know some things to be true about this object. I know it's in free fall, so I know its acceleration is negative 9.8 meters per second squared. I know that. But I also know something about the ball up here. Okay, let me go get a ball real quick. If I throw a ball up in the air, what's its velocity at the very top? 0. Okay, because the ball has to stop before it can fall back down. It stops going up before it starts going back down again. And so for that split second, I know the velocity up here at the top. So I'm going to call the top my final point for this calculation, and I'm going to say my final velocity at that point is 0. Okay, and if I know the velocity here and the velocity here, I can certainly figure out my displacement at that point. Okay, and that's what I'm going to do, the height that it reaches. So what is my displacement? That's what we're looking for. So we have VI, we have A, we have VF. Again, only one of those numbers was given to me. That's why these questions can be tricky. You have to think, what else do I know? Even though it's not written, what else do I know? Okay, and so now we're going to take a look at our equations again. Which equation should I use in this particular example? Take a moment, look at your variables. Which one should we use? I can certainly use A if I want to solve for time. I can find time with A. B. If you want to find time first, you can. There's nothing wrong with that, but that's not what you're asked for. You can find time and then find delta x. However, if you want to do it in a single step, you're going to want to use equation B because look at those variables. Here's my VF, my VI, my A, and delta x. That will allow me to solve for delta x. Okay, we can't solve for delta x with equation A because it's not in there. All right, so we're going to use equation B. VF squared equals VI squared plus 2A delta x. Substitute in, looks like this. 0 squared equals 3.4 squared plus 2 times negative 9.8 times delta x. Solving, okay, that 3.4 squared is 11.56, but I'm going to subtract it to the other side. So I did 2 steps at once, I apologize. 3.4 squared is 11.56, but I need it, again, I'm trying to solve for this, so isolating it means subtraction, so I end up with this. Negative 11.56 equals 2 times negative 9.8 is negative 19.6 times delta x. If I want to solve for delta x, I need to divide both sides by negative 19.6. And when I do that, I get a displacement of 0.59 meters. So that would be the height that it reached. It didn't go very high, okay? 0.59 meters. Does anybody have a question about this problem? I'm gonna tell you right now, the trickier question that you'll see sometimes isn't this. Instead, it's how long was the ball in the air? I didn't ask you that here, and I don't know if I have one of those in here or not, but the trickier question is how long was the ball in the air? Because if I solve for the time here, if I find the time that it takes to get here, is that how long the ball is in the air? No. Exactly what you do. Okay. If you figure out, if you use this value of 0 and you find the time to that, that's only half of your time because it has to go up and then back down again. Okay, so if I ask you for what's the air time or the hang time, we'll see that sometimes, you can find that time and then multiply it by 2. Yes, sir. No. What would my velocity be here in this example? If the ball at this point is going 3.4 meters per second, how fast would it be going just before it hits the ground? What do y'all think? If I throw the ball up at negative 3.4 and I catch it again just before it hits my hand, how fast is it going? Does anybody know? Negative 3.4. If I throw it up with 3.4 meters per second, it will be moving back down with the same velocity, opposite direction. Okay, same magnitude of velocity, different direction. Okay, so I do actually know something about the end point as well. You could use that if you wanted to. Okay, so it's up to you how you choose to solve these. There's more than one way. But to find max height, I do need to use this point because that's where the height is. So I do need to use the velocity up here at the top. Here's that question. How long is the ball in the air? Okay, so if I want to find the time, we already talked about how to do this. Okay, I know my initial velocity. I have the final velocity up here is 0. So I'm going to find the time, but this is just going to be the time up to the top. Okay, and I could have actually used multiple different equations, but I'm going to use this one. VF equals VI plus A times T. And if I plug in, I have 0 equals 3.4 plus negative 9.8 times T. Again, I'm trying to isolate T, so I'm going to subtract 3.4 from both sides. Negative 3.4 equals negative 9.8 T. Divide both sides by negative 9.8. And that is my time up to the top. That's not my whole time. And then we have to do what Mason said, we have to double it. Okay, so the total time would be that times 2, which is 0.694 seconds. Okay, that's the trickier question because you have to do that little extra step. And don't forget about it. Okay, make sure you pay attention to the point that you're using, because if you're using this point up at the top, that's only going to be half your time. But you can find it, you just have to double it. Questions about this one? Okay. All right, so let's talk about what our graphs look like. You guys did a bunch of graphs yesterday in the card sort, and one of them was actually the graph for this scenario. If I wanted to talk about my position time graph, this ball starts out moving upward and slowing down. So that's going to be my positive direction, but my slope has to get flatter. And then it's going to start going down and speeding up. And so my slope's going to go from this flat part at the top to a steep slope going down. And so it actually looks like the trajectory that's drawn up here. If you have an object thrown up in the air that comes back down, you get this shape. That was one of your shapes yesterday. Guys, what's the acceleration of this ball? Why does it do this? Why does it come back down? Gravity. Is gravity changing? No. Okay, my acceleration is going to be the same the whole time. My velocity is going to start out faster. It's going to slow down moving forward, and then it's going to speed up going backwards. It's the same slope the whole time. It has to have a constant slope because I have constant gravity, but it starts out in the upward direction, so that's the positive region of my graph. It goes to 0 because it reaches that max height where it's 0. Okay, and then from 0, it speeds up going down. Okay, that's exactly what this line shows. It has a negative slope. Specifically, it has a negative slope of negative 9.8. In fact, if I wanted to like number this, that's where this line would be, negative 9.8. Because I threw it with an initial velocity. Okay, so it has an initial velocity and then it slows down, stops, and turns around. So it has positive 3.4, slows down to 0, and then speeds up as it falls. Any other questions about my graphs? Again, y'all saw those yesterday. By the way, if you didn't get those paired correctly, that's what they should look like whenever you do the guard sort. All right, here's another example with a graph. It says the velocity time graph shows data for a penny falling from the observation deck of the Empire State Building in New York City. How far has the coin fallen after 4 seconds? You could calculate this, or you could use my graph. Okay, so looking at my graph, if I want to figure out how far, I just have to find area. This is the velocity time graph, area between my x-axis and my data. We call it area under the curve, but it's between my x-axis and my data. Okay, so at 4 seconds, it's this triangle right here. So if you find the area of that triangle, that will give you your displacement. Could you calculate it using kinematic equations? Absolutely. This is probably a little bit faster. Okay, and so you would do 1/2 base times height, 1/2 4 times negative 39.2, and that'll give you your answer for how far it has fallen in 4 seconds. I don't have the answer on here. Okay, and if you want to practice with this one, if the observation deck is 320 meters high, how long will it take the coin to hit the ground below? You're welcome to try that and see if you get that value, 8.08 seconds. If you feel like you need some more practice, please do that. If you feel comfortable with this stuff, okay, then the next thing you're going to be doing is working on your assignment in my open math. Okay, so you're welcome to start on that now, or if you want, you can instead take a look at this question, try it out, and have me come check it. If you don't get 8.08 anyway. If you get 8.08, you're good. Okay, but otherwise, for the rest of the period today, all you're doing is working on the My Open Math assignment, and that assignment is, let me get the exact name of it because I don't remember, is 202.3 Mixed Kinematics Problem Set. Okay, so that's the one you're working on today. Tomorrow, you are going to have a CFU. Okay, that's like our quiz, but it's in My Open Math and you can talk to each other. We only get 1 attempt. Okay, so you do have that tomorrow because your unit test is on Monday. So we're going to do our quiz tomorrow, our CFU. We're going to talk about it, review on Friday, and then you guys have the weekend to hopefully maybe look at your stuff a little bit more and not forget everything. Okay, but you have a test on Monday morning whenever you come in. Okay, so again, go ahead and get to work. If you have questions as you're working on your My Open Math assignment, or if you have questions about the questions that are currently on my screen, please let me know.